Good evening, good afternoon, good morning, depending on where you are, everybody. I'm Albert, and when Bastian invited me about this talk, I decided to. I thought about what direction should I take the talk, and I figured I would maybe highlight my perspectives on African water resources with a focus on ambient river water quality, and I will highlight here modeling from catchment to global scale and also remote sensing. And I know it's Friday, so I will not take all the 40 minutes. I'll probably take around 20 or hopefully less to go through my talk. As I will start with highlighting, this invisible water crisis, as mentioned by the World Bank. So globally, about 3 billion people are at health risk due to scarce data on water resource, according to the United Nations Environmental Program. But by water quality here, we refer to the chemical, physical, biological characteristics of water that, of course, determine the suitability for its particular use. Now, as you can see, there are multiple water quality. You could call them constituents, variables, parameters. But in this talk, I will mostly lean towards nutrients because that's where mostly my specialty has been through sediments and nutrients, and this will mostly come out through the talk. So, according to the Uppsala conflict database, they highlight that unsafe water kills more people than disasters and conflicts combined. But when we look at the geographical spread of deaths attributed to unsafe water, we see that these rates are more in low-income countries, particularly across sub-Saharan Africa, where about less than 1/3 of the population uses safely managed water. But the way we track this water quality mostly is through the SDG, so SDG 6, the Sustainable Development Goal 6, which recognizes the need for access to water and sanitation for all. What we use here is mostly the indicator 6.3.2 that monitors the proportion of water bodies with good ambient water quality. So the ambient water quality will be defined in the subsequent slides, but the SDG focuses on 5 main parameters of water quality. So it looks at oxygen, salinity, nutrients, so nitrogen, phosphorus, as well as the acidification. Now, when we look at the recent report from UNEP, that tracks this good ambient water quality, and here by good ambient water quality, they mean that water that is safe for ecosystem and human health are functioning. The report highlights key messages such as no reported values for most countries in the global south, and also lowest income half of the country had less than 3% of the total observations, so the measurements. And most interestingly is that nutrients, so the nitrogen and phosphorus, failed to meet these targets more often than any other water quality parameter that is measured within this SDG tracking. So when we go to the African continent, what do we know about its nutrient concerns? Well, there have been scattered reports about eutrophication. So this is where you have, a high increase of nutrient loading into a water body, and then you have these algae blooms popping up. But not just in inland waters, but also on African coastal waters. So about 20 occurrences of eutrophic hypoxic sites have been reported along the African coast. And this is where these red dots are that you see on the African coast. But when we go into the database of existing water quality observations, and we look at the African continent, we literally see, first globally, we see an uneven distribution of in situ observations, both across space and time. But when we zoom into Africa, we don't see much of the observations, and also the existing observations are mostly located in South Africa, which accounts for 97% of all data in sub-Saharan Africa. And Africa as a continent accounts for only 4% of the total observations of water quality, while 71% of this data from the stations is located either in North America or Western Europe. And so that's why we try to come in here using modeling, and as well as also show you later Earth observation on trying to closing this gap and hopefully informing UNEP on how we can track the progress towards SDG 6 using this indicator SDG 6.3.2. But in areas where we do not have observation data, can we close this gap through modeling or observation? Now, starting with modeling, personally, I work a lot with the soil and water assessment tool, And this is a process-based, physically based model that simulates both the quality and quantity of surface and groundwater and can be used to predict the environmental impact of land use, land management practices, as well as climate change. And it's mostly been applied at a catchment scale, but what we did here is upscale it from a catchment scale onto a continental scale of Africa, and later, as I will show you, onto a global scale. So the way the conceptual modeling process of water quality here is that we start with the hydrological setup of the model, and then we try and add in pollution sources, so both non-point sources of pollution. And here you can account for agriculture, you can account for atmospheric deposition, and also runoff from natural environment. But then also point sources which mostly account for wastewater discharges. And then you do a hydrological calibration focusing on the mass balance components, and then later a water quality calibration focusing mostly on nutrient balance processes that occur. Now, just to highlight here is that within the SWOT model here, the fate and transport of nutrients, so nitrogen and phosphorus within a basin or catchment depends on nutrient cycling in the soil environment and the river phase, so the river channels. And the model here simulates nitrogen phosphorus cycles, tracking various inorganic and organic forms of both nutrients in the nutrient pools that are simulated. So the way the SDG indicator 6.3.2 is calculated according to the United Nations Environmental Programme is that if 80% or more of its monitored, so these are the observation values, meet their targets, then that water body is considered to have good ambient water quality. Now, the UNEP allows countries to set their own benchmarks for the different water bodies. But for the African continent, since we do not have these, we use the optional benchmark set by UNEP, which sets the benchmark for total nitrogen and total phosphorus at 0.7 and 0.02 milligrams per liter. And these are a bit conservative. But since different countries do not have their own set benchmarks, we focus on the optional UNEP target benchmarks. And what we do here is that for the African continent, since we don't have the monitored values, we replace the monitored with the simulated values and try and determine the proportion of the daily simulated values now, as opposed to observed. And we use 2010 and 2019, and we estimate values that fall below these target thresholds for both nitrogen and phosphorus. So the way we set up the model here is that we use existing global data sets. If you've not worked with SWOT, it ranges from the digital elevation model through land use, soil, climate data, reservoirs, management practices. It's mentioned by a few. And you can check out this paper, this work that was led by Tawan and me, where we set up this model first, looking at water resources, the hydrology in Africa, and calibrated it and evaluated it using mass balance approaches, so focusing on the mass balance components. And then later, we also added in the nutrients, so the pollution sources. And the way the SWOT Plus works is that the smallest unit of application is called an HRU. So this HRU is the hydrologic response unit. Now, for an agricultural HRU, what we do here is for each HRU, we determine the management practices used from the global data sets. So that is the planting and harvesting of a specific crop, the fertilizer applied, the manure applied, the irrigation, if it is irrigated, and we apply it for each HRU. So if you work with spatial data, so assume like a pixel. So for each pixel, you apply that if it's an agricultural pixel. And for all the other HRUs, we apply the atmospheric deposition. And then the point source, of course, this is applied directly into the river system. And then we run our model and evaluate it. As you will see here, we evaluate it for total nitrogen and total phosphorus. We did not have a lot of data. It was already highlighted. So most of this was done in South Africa, as specific, to be specific. Now, after the evaluation of and calibration of nitrogen and phosphorus, we try to estimate the SDG 6.3.2 for South Africa using the observations and also using the simulated values to see the compliance, whether we would achieve the same compliance as the observations. And we found that model estimates had a compliance of about 78% and 90% for nitrogen and phosphorus, respectively, meaning that we Model simulations closely align with the observed values on achieving similar river classifications for this SDG compliance. And then what we did now, we extended this SDG indicator calculation to the whole of Africa. And as you can see, we found out that one third of African rivers, so about 33% of the rivers, fail to meet this good ambient water quality standard defined by UNEP. And but then we found that 45% of the rivers did meet for TP, while 14% did meet it for TN. So TP was mostly performing. We don't achieve a lot of compliance with total phosphorus as compared to total nitrogen. And we went into deeper to determine what could be causing this. And we could see that areas where where we did not achieve a lot of compliance coincided a lot with a lot of fertilizer and manure application, a lot of wastewater discharge, but also areas with low dilution capacity in terms of precipitation. So dark spots include the Niger Delta, the Nile River, the Orange River, but we had some bright spots in the Senegal River where we did not have a lot, where we had a lot of compliance with the SDG indicator. But something that also stood out was the Congo River Basin. So throughout literature, getting studies or finding literature that has been done in terms of water quality within the Congo River Basin was really, really scarce. So that's something that we could also highlight from just digging into literature. So some takeaways from this, it's just specifically for Africa, we found that one third of African rivers failed to meet this good ambient water quality nutrient standards. And the rivers that did not meet the standards coincided a lot with areas of high fertilizer and manure inputs, as well as high point source loadings. And of course, implementing strategies that target this could be crucial for Africa. But also interestingly is that majority of the rivers, so 67% are still in good condition, which provides an opportunity for shortcutting further pollution along the African continent. So just to also highlight, I added this slide to just highlight some of the ongoing works that we do in Africa. And this SDG mapping, we've expanded it beyond nutrients. Now we've added in also BOD as well as water temperature, and also projected it to see if we will achieve this SDG 6 by 2030. And we also check at 2050 and also 2100. We've also done an attribution study to look at the different influences on water quality. So we disassociate climate change, land use, point source, and fertilizer change to see what could be driving nutrients within the African continent. And also we're looking at, we've also linked this nutrient pollution with biodiversity, but specifically looking at freshwater fish species to see the risk of these nutrients on biodiversity. And most of this work is now currently being reviewed. Now, from the African continent, we figured, okay, we became very ambitious and decided to upscale it globally and look at a global water quality model. So to just also quickly highlight that. So this model is set up on, what we did is we split globally the continent into 90 large basins, which we run in Palaro, and we run this on a supercomputer that is hosted in Brussels. And we first did the hydrological setup, just like we did for Africa, and evaluated it. And then later also added using the same workflow, added these pollution sources to be able to run for water quality. And when we looked at the evaluation, so we situated our global model with the existing global nutrient models, and we could see a high correlation in terms of predicting the loading for the major rivers globally. We also evaluated our global model with the existing observation from the GenStat database to see how it would perform. And here we're using the KGE and normalized root mean square error. And we could see it was performing well in certain areas, but also in other areas, we had a lot of room for improvement, which is, I guess, common around a global water quality model. So this was the first version of this model, and we mostly produced it to be able to participate within this intersectional ISMIP water quality modeling framework. So we applied this model in a study to look at future nutrient reduction needs in the world's largest rivers to limit coastal eutrophication. So what we did with our global model here is that we selected the world's largest 24 rivers, and then we estimated how much reductions are needed to avoid the risk of coastal eutrophication. So we selected river basins that are greater than 400,000 kilometers squared, with an annual average discharge exceeding 3,900. And also most of these rivers we selected are already affected by eutrophication. So when you look at literature, you find that there are studies that look at, current nutrient loads, there are studies that look at future nutrient loads, but they're literally limited to zero studies that look at backcasting procedures, which estimate reductions needed to avoid, to limit coastal eutrophication. And this is the novelty that we bring in here. So we try to estimate how much reductions do we need to avoid coastal eutrophication globally for these 24 large rivers. So our approach is that we use a multimodal ensemble. So we associate it with the two other existing global nutrient models, and we have an ensemble of three models. We look at nitrogen and phosphorus, and then we also look at only one emission scenario. So from our multimodal estimates, we find that nutrients are expected to increase: nitrogen by 17.9%, nitrogen loads, and phosphorus loads by 21% by 2050. And you can see that most of these increases are projected for the African continent and a few basins within Asia. So when we do this, when we use the indicator for coastal eutrophication potential to estimate how much reduction is needed, we find that globally, we need 67% reductions in terms of total nitrogen and 64% for total phosphorus. But some rivers stood out. For example, the Nile, the Niger, Ganges, the Ganges, San Francisco, all these rivers will require reductions that exceed about 50% for both total nitrogen and total phosphorus. But also interestingly, some rivers like the Irrawaddy that are projected to also experience some significant increases in nutrient loads by 2050, they do not require major reductions. And this could be the ratios of nutrients to nitrogen, phosphorus to dissolved silica. So that was just quickly to highlight the existing global models, and some takeaways from this work is that there are global agreements between the models, but there's a huge there are differences locally, whereby we could see that all models project increased NNP loads, but then they show some mixed results at river basin level. This is, of course, inherent due to the structural differences, also some differences in input data, and also differences in the space on this spatial scale of how these models are run. But the advantage is that we're using a multimodal mean, which sort of improves our confidence. And then we also notice that there are urgent reductions needed for major rivers. Now, I wanted to highlight that most of this work here in the global modeling has been undertaken within this initiative in ISMIP. And I would advise you check out this work with this work this paper that has been led by Stockholm Marina, where we brought almost existing global models, also some regional models, and looked at different model interdifferences between global models and with regional models and global models and global models. And I think if you also would like to be part of this, it would be worth exploring. If you have a global original model that you can submit your simulations in here for an intercomparison, it is very much welcome. Now, the last thing that I would like to touch on is the Earth observation. So estimating this SDG indicator 6.3.2 using the Earth observation. So like we've already highlighted, in some areas you don't have observed data, and maybe you also cannot set up the model. So what do we do? Now, we had this work that we did under the World Water Quality Alliance seed funding. We try to use remote sensing to also track this SDG progress. Currently, there's only three water quality variables that exist through remote sensing. So you have turbidity, chlorophyll A, and water temperature. So we try to use free and open access Earth observation data. And then during this work, we also had we interacted a lot with focal points from UNEP in Burundi, DRC, Tanzania, and Zambia, because we tested this proof of concept on Lake Tanganyika. And uh, the way we went about using remote sensing is that ideally you define a target water quality, and this could be through baseline, threshold, default, or a national target value if you have it from the national database. And the water body can be considered good, is considered good or stable if it's better than the baseline condition, or and for the if you're using the target value, if it is equal or above the national target value, and in the opposite direction, it's considered bad if it is below the baseline condition or it's below the national or target value. Then you calculate the number of measurements per pixel, which are met by this water quality target value during the reporting period for each water quality parameter. And then in third step is that you combine all these number of measurements, which make the target value for all the water quality parameters. So you have the different water quality variables. And then in step 4, you classify whether it's good or bad, depending on whether the majority of the water body is within this target range over the reporting period or not. So this is just a schematic of how we get chlorophyll A, turbidity, water temperature. I hope it's somehow clear in your screen. And then we go through these steps until we combine it into this binary form, because UNEP reports on the binary form. It's either good or bad. There's no in between. So when you look at Lake Tanganyika, what we found out was that 92% are of the lake fell within the conditions, where we fell within a category of where conditions sometimes departed from the baseline state. So between 2017 and 2019, 67% of the satellite derived water quality measurements met their values. But this is below, if you remember, the compliance is 80%. So this is below the 80% compliance required for good water quality classification. And you can see here that the northern part of Lake Tanganyika is where it's mostly predominantly reddish or brownish, and that is where it has the highest risk or the lowest performance in terms of this good ambient water quality condition. So some takeaways from this is that with remote sensing here, it sort of enables the evaluation of this ambient water quality for a water body without requiring any other source of data, which could enable low-income countries to report more widely on SDG 6.3.2 and have information about the ambient water quality of their water bodies for management decisions. But then also the indicator, the challenge is, of course, the indicator we did not evaluate it against any in-situ data, although the input Earth observation products have been validated and delivered with some uncertainty measurements. But overall, this really shows the added value of the Earth observation data for reporting of the SDGs here. And you can check out a summary of this work there. And I think that's more or less that I would like to share, because I know it's a Friday and probably everybody's a bit over the edge. So I thought I would keep it within this time frame. And thanks a lot for listening.